So in the previous, you can see the board, right? So in the previous lecture, we were discussing about the photon propagator, and we showed that the equation that one needs to consider is the following. We consider the Maxwell's equations in the presence of a source, and then if we just use the definition of the field strength tensor, then that will lead us to this equation. And then what we can do is the following. We can basically write down the corresponding equation of the Green's function of this equation of this differential equation. And that we have written in this form. This is the difference between, we have taken it to be a difference between x and x prime. For the simple reason that the Green's function should have translational invariance. And now we have. So from here, we, in the previous discussion, we showed that this will not lead us to a propagator. We could find in the last discussion that this did not lead to a propagator, or we found that the propagator in this theory is undetermined. We cannot determine it in a consistent way. And the way out was the following. We modified this equation the following way. Just put in a factor. This operator, this is the modification factor. Now, we just find, and now what we found in the last class was that we are able to find the form of this propagator, and the method in which we proceeded was the following. We made a Fourier transform of this, and then we got an equation involving d mu mu k, this is the second line tensor. And then we took an ansatz for this, put of this form, plus d mu, and then we consistently determined d and d. It showed that d mu mu can now be determined. And I said that this modification of this equation in this way is basically nothing but gauge fixing. So let us see what we mean by that. So for that, let us consider the action of a fluid. So let us start with the Maxwell action. And now, this is basically nothing but equal to x. Using the definition of the field strength tensor, that will lead us to the following. Okay. Now, just need to multiply. That is simple. Multiply this uses. It's just straightforward multiplication, and now it's quite simple to see that this term and this term just adds up. Okay, so you can just do the 2, get rid of this, and this term adds up. You can just the 2, this will make it 0. Okay, this term adds in this term. Why? Just change mu to mu and mu to mu. That is this term. So that is why you get a factor of 2. Here also change just mu to mu and mu to mu, and you will find that this term is also the same, that will be a factor of 2. So now if you take that 2 out, this will make the 2 here. So far everything is fine. That is just simple manipulation. And now what we can do is the following. Let us look at the second term. Let us look at this. So second term is d4x and I'm just taking the sign inside. So this is basically del mu, del mu, and del mu, del mu. That is what I have started. My notes I have started it in this way. So what I shall do is the following. I shall take this mu downstairs. Okay, the second one. Just taking. Now this term I take as total derivative. Take the side. Total derivative is this. And then I have to subtract the term and subtract this. Let us look at this term now. You will understand why I am doing this gymnastics. It will be clear in a moment. So this term, I can now write it down as L. So what I can do is I can put this on the top, take this the bottom. Then if I take del mu, this will be just to a del mu. So I have once again written it as a total derivative, but then I have to again subtract. But minus and minus, this will be plus. What I need to subtract is the following: del mu, del mu. Okay. Is it clear to everyone? Online?
Sir, where is the first term? Uh,
Which one?
Del mu nu, del mu nu.
Which term? In this line?
Other side of the board, first term, last line.
First term I am not writing. This one.
Okay, okay, okay,
Term I am not writing now. I am just looking at the second term.
okay, sir.
Okay. Okay. So now if this is fine, then you see these are basically total derivative terms. So you can integrate them, and these will demand that the surface is at infinity and the fields at infinity vanish. So at the surface the fields vanish. So these are total derivative terms, these will vanish at infinity. So what remains, so what I am basically doing is I am showing away the boundary terms. So these are basically, if you apply the Gauss divergence theorem, this will give you surface integrals, Therefore, at the surface, you are throwing them out, so you are basically throwing the boundary terms. So what remains is the bulk term, which is this term, and this term is nothing but del mu a mu whole square. Okay. So let me go to the other side of the board now. So now you can see the full board. So what we have now found out is the following: the action is minus half integral before x. Now this is the first term that we were talking about. So I am now writing it down. This is basically the mu del mu. So this is the first term. This is I have written it right here. And then the second term. But second term is this term which I have simplified, and it is nothing but minus the term that I have already found there by showing out the boundary terms. The action, Maxwell action is basically this. So let me just zoom this. Okay. So this was the starting point, 1/4 mu, and now this action has been simplified to this following form. But we should remember one thing: it is important that this action will give you the same equations of motion. We lead to the same equations of motion, but this action, strictly speaking, is not the same as this action because we have thrown the boundary terms. That is what we have done. The boundary terms are not there. And you can check for yourself, please check whether you get same equations of motion from this action. You will obviously not get the source term, because this does not have the source. So what you need to do is add a source term. Then you will get the source term in the Maxwell's equation. Please check it. So what I would ask you to do is the following: just functionally differentiate the action with respect to the gauge field, obtain the equation of motion. And this will be the same equation of motion that I have obtained from this one. Now, you see that with this action, I have just thrown out the boundary terms, but now what you can do is, in this action, you just, so let me call this action as SM, Maxwell theory action. This is also SM, but this SM and this SM are a little bit different because we have thrown the boundary terms. Now, let me define a new action, which is the original action SM. Then, this is plus or minus half let me find a new action which is Maxwell theory action. Right? If you do that, the full theory, if you write down this, if you just simplify or put in this SN here, then what you will get is the following. That's half x. Then So what we shall get is this action. If you add that term, this term that we have added here is called a gauge fixing term, or you can call this term, this full term, as SGF. And you can check that if you again calculate the equations of motion, compute equations of motion by functionally differentiating this case with respect to the gauge field, you will precisely get the equation that I wrote down. So that equation can be obtained from an action, which is basically the Maxwell action plus the gauge fixing term.
Is the same equation of motion just with each ingredients?
You calculate the equation of motion, compute the equation of motion from that action, you will get the same equation that I wrote down there. Yes, you will get that factor there. You will get that factor there. Now about the gauge fixing. Why is this a gauge fixing term? You can actually show by using the gauge invariance of electrodynamics that you can fix this term to 0. That you can do. You can consistently do, everything will remain the same. So putting in the term of this form in the action solves the problem, right? Because this gives you the correct equation of motion, and now there is no problem in finding out the propagator. The propagator exists now, and the addition of this term in the action is basically nothing but you are fixing the gauge fixing term that you are adding in the action, and that solves the problem. So this is the thing that I wanted to show you, that Maxwell theory, in order to get the propagator, what we need to do is the following: we need to gauge fix. Otherwise, the propagator will not exist. And the reason is very simple. It's simply because of the fact that there are too many unphysical degrees of freedom in the gauge theory. Therefore, we need to get rid of those unphysical degrees of freedom. That can be done by gauge fixing. That will only lead to the physical degrees of freedom. Once you do that, once you are in the physical sector of the theory, then the propagator is completely verified. And this completes our discussion for all the propagators. We have discussed the propagator of the real scalar field, the complex scalar field, the fermionic field, as well as the electromagnetic field. And we know that the propagators are very important for the study of quantum field theory, because we need to know how the particles move in space-time, and particles moving in space-time describes interactions. When they interact with each other, so they describe interactions, we need to know how they move in space. And that is why propagators are very important. So today what I shall do, since we have completed all the propagator, we have discussed the propagators of all the fields so far, except the non-abelian gauge field. We have not touched. There is another field, right? Non-abelian. And also there is gravity, graviton propagator. Gravity we shall not touch in this course. Gravity you will study in some courses later on. For those who are doing projects, they may get some introduction to what gravity is. But we have not looked at the non-abelian gauge field propagator as well as the gravity propagator. We have looked at the scalar field, complex real scalar, complex scalar, Fermi, the Dirac field, and the electromagnetic. So, as an aside, before I start a new topic on Monday, what I shall do today is I shall tell you something about a little bit more about the topic. So suppose, let us consider this Schrodinger equation. Let us consider this Schrodinger equation. This is the Schrodinger equation, right? And this is the free Hamiltonian. There is no potential. That is why I have written it as H0. We have been looking at difficult theories. We have not looked at non-relativistic theory. This is a non-relativistic. We should not say non-relativistic now. This is basically Schrodinger equation, but as I mentioned earlier, whether it is relativistic and non-relativistic, it depends on the form of the Hamiltonian. But what we shall do is, we shall indeed take it to be non-relativistic because we shall take this to be b square by 2. Then it is non-relativistic. But if I take it to be square root b square plus c square plus n square c to the power 4, then it is relativistic. But we shall look at this theory. And we have not found the propagator for a non-relativistic field, non-relativistic quantum mechanics. We have not. We have actually found the propagator for non-relativistic quantum mechanics also when we discussed the path integral groups. We have actually found it out for the free particle and the harmonic oscillator. But let us again see, look at this thing more carefully. So here also you can immediately define a Green's function. What we can do is only this is your operator. So in the minus or plus, it doesn't matter. Let me see what I've taken, what sign I've taken. So this is our Green's function equation, and we can take a Fourier transform. Once again, we call this G.
Sir, can you please focus on the left side board only?
Yes, yes, sure. Okay.
Okay.
So what we are doing is we are looking at the Schrodinger equation, the non-relativistic Hamiltonian, free Hamiltonian b square by 12, and we are just writing down the Green's function for that. Now the standard technique is to take the Fourier transform. Now if I just put this over here, then what we shall immediately get is the following. We shall get b over p. Pi over 4, and then so when this acts there, omega that is equal to the delta function. And from here we can immediately get the delta. That's what we should do. Or it is better to like because you should remember that the P0 is not related to Pi. These are independent. So this is the Green's function in the momentum space, and therefore you can immediately write over to Green's function. So here omega is basically the P0 component, right? So here get P G0 P, the substitute for G0 P is get as before what we were getting earlier also for the real scalar field. The approach is same. We get this as Green's function. Here is omega. So there are two integrals, dq d omega c by rho 2 by e to the power of minus I e minus I. So this is the Green's function for the non-relativistic P non-relativistic particle. This is what we get. From here, we can immediately see that there is a pole. When you try to integrate omega from this to this, you can see that there is a pole. And the pole you can easily read out. This is this by 2n. So there is a problem in integrating from infinity to plus infinity on the real axis. And so the standard description, although this was not done in the context, this was basically done by and this formulation of non-reductive path integrals. But now we are looking at this same problem in a different way. So what we can do is once again in the same spirit as Feynman did in the case of the relativistic field theories, that you can avoid integrating or you can avoid this pole lying on the real axis by defining a new Green's function, which is nothing but all this stuff that you have here, this exponential stuff here, and just avoid this epsilon is a very small positive number. So now you see that this was the Green's function, this is the Feynman Green's function, where we have used the I epsilon restriction, Feynman restriction, epsilon restriction. And what this does is nothing, basically shifts. So this is the imaginary omega axis, the real omega axis. But by by defining a new Green's function in this way, the pole is now initially it was at this point, now it is shifted to this point. This is what right? And our aim is as before, we want to do the omega integral, and for that it is easy to do. You know how to do it. So it's a very simple complex integral. And as before, we consider say p minus 5 greater than 0. Consider this. Then from this integral, if p minus t5 is greater than 0, then we can see that we need to close it in the lower half, otherwise it will be a problem. And in the lower half, it will get the contribution from this pole. And if t minus t5 is less than 0, we have to close it in the upper half. Upper half there is no pole, so the result will be 0. Right? There, if you do this simple integral, it's very simple to do. What you will finally get the following. I shall not do it. You just write the result for you. But you can, this is just one line. You can please do it immediately. So this will be minus I theta t minus t prime integral by q into Can you see this, or should I do it? You want me to do this integral? Don't want, but this is for one. What is the general consensus? Do you want me to do? No. Others should not feel ashamed. It's fine, good. And what about the online guys? You can do, you are fine. It's good that you can do it yourself. And what about the online people? You can do it yourself, I guess. So it is very simple. For this, you just close it here in the lower of plane, and then you get this residue. This is simple code. Apply the formula for the simple code, then you will get this result. And here you should remember that this here also there is. So let me just expand it like this. So we have a dq p by 2 pi by q. So this will give us a t dot x minus x prime. But now this is written, although this is non-relativistic, but we are writing it in a relativistic 4-vector notation. That's the power of this. And you will see that this P0 is now related to the this P square by 2m. This is nothing but P square by 2m I. And this we have actually already derived earlier, the path integral force. And now this is a very simple Gaussian integral in P vector. So P vector mod, P vector mod. So it's a very simple Gaussian integral, and you can perform this Gaussian integral, and you can find out what the result is. You know the result already. Not only that, you can also write this thing in a very nice form. So that is quite instructive to write. And we have actually written the result earlier also in that form. So remember the path integral force. But what we can do is we can write this as I prime or I star, where phi px, so let me write it here, phi px, nothing but 1 by 2 pi to the power 3 by 2 to the power minus I to the x. So if I define this in this way, phi px, this is what? This is basically the plane wave basis. If you define this as some function, which are basically form an orthonormal set, then you can see that you can write the green function very nicely. And what this result is basically saying, this we have already learned in our mathematical physics course. This result is nothing but this is the eigenfunction expansion of the Green's function that we have already learned in mathematical physics course, and this result is just displaying that result. That Green's function can be expanded in an eigenfunction basis, and that we have precisely now shown in this context. So that is, everything is fine, everything is consistent, and you can, as I mentioned, that you can go on to calculate this integral now, which is the Gaussian integral in mod P vector, and this result is also quite well known. I'm not writing it down. If you want me, I can give it together, but this we have already calculated for the 3 pi. But what is important from this result, what I wanted, so you can already make so many observations that the Green's function can be expanded in an eigenfunction basis. You can do the integral exactly, things like that. But what is important from this result is the following, that what you want to find is, you want to find this Let us go back to the Schrodinger equation. I'm calling this as the Schrodinger equation, non-relativistic Schrodinger equation. Let us go back to this. And if you just put in a source, then you can basically write down the solution of this equation in terms of the Green's function, right? That means if I simple, so the homogeneous thing, minus or plus whatever it is, then this will be the Green's function, G0 x minus x prime, x prime, prime. Solution will be something like this. So we know the Green's function, find out. And this was precisely the propagator expression that I wrote down in the first class of the path integral course. So now you can see that this propagator that you have, this contributes, and this is a positive energy solution also. You can see that this is positive energy solution. You have a class after this. Okay. So this is a positive energy solution. And what it tells is that you precisely get the retarded Green's function here. You don't get the advanced Green's function. So the positive energy solutions are basically moving forward in time. You can see it from this equation. Because this contributes only when t is greater than t prime, right? There, so this is your t prime. T prime is getting integrated over. T is always greater than t prime. Only then this expression contributes. This is a positive energy solution. So the positive energy solution is moving in the forward direction, and therefore this is a retarded Green's function. This is not an advanced Green's function. And that is what you want, because you want causality to be maintained. That is fine. But let us now come back to the real scalar field propagator. 1 second. And we have calculated the real scalar field propagator explicitly in this course. So in the real scalar field case, we started out from this equation, then we wrote down the Green's function, the propagator, then we found out the propagator, then we found out then we used the epsilon prescription of Feynman and wrote down the Feynman's Green's function, and then we can immediately write the solution as the Feynman Green's function is then denotes Feynman x minus y. And we have actually calculated what this expression for the Feynman Green's function is. Basically, e minus e prime integral into p by 2 to omega t equals this same thing, same measure, and this is the result that we have calculated, and we have done it for the Dirac field. Now, in this case, at once you see that something funny has occurred, right? This solution is perfectly fine, because if I put it over here, then this tells us that t is greater than t prime. This is a positive energy solution. This is positive energy solution moving in the forward direction, right? But what about this solution? This is a negative energy solution, right? It's negative energy. But if you put this over here, this is basically y0, t prime means y0 prime. So it basically tells us that this is a negative energy solution, but this time is smaller than this time over which you are integrating, right? So, although this solution is a positive energy solution moving forward in time, this is a negative energy solution which is moving backward in time. So something very, what should I say, what very funny is occurring here. Feynman-Green's function is giving us something which is telling that, but one thing is good in the sense that this is not a positive energy solution moving backward in time. Then that is basically an advanced Green's function, which we throw away in Maxwell theory. In classical physics, we throw it away. Positive energy solution moving backward in time. What do you mean by that? It's a problem, right? But this is also a problematic thing. This is a negative energy solution moving backward in time. So this actually tells us. So Feynman interpreted this in the following way. It appears that as if there is a new form of matter, which is negative energy solution moving backward in time. So as if there is a new form of matter, which is positive energy moving forward in time, but it is not really matter; it is antimatter. So that was Feynman's interpretation of this solution. So you can interpret this negative energy solution moving backward in time as a positive energy solution forward in time, but it is something different from matter. It is antimatter. So that is the Feynman way of understanding what antimatter or saying what this negative energy solution is. Usually, what happens, as you see here also, you don't get the negative energy solution. But negative energy solutions always appear, but already encountered, whenever you study a relativistic theory. For example, Dirac equation, you will always encounter negative energy states. Dirac equation, any relativistic theory. And in field theory also you have negative energy states. But it comes with another thing that it's a negative energy state, but it is moving backward in time. Therefore, it can be interpreted, you can just turn it around and interpret it as a new form of matter, which is positive energy moving forward in time.
Sir,
Ah,
following this interpretation, it should be that at the beginning of the universe there should have only been antimatters.
right?
I am trying to say that if antimatters move backward in time, that means that at the beginning of the universe, there.
Antimatter is not moving backward in time.
Okay.
Antimatter is moving forward in time. This is negative energy state, which is moving backward in time. And therefore, positive, just the opposite of that is positive energy state, moving forward in time. But this is a new form of matter. It tells you that okay, this is not matter, but this is antimatter.
Okay.
Actually, in the universe also, in the context of universe, at the beginning of the universe, just at the Big Bang, at the time when Big Bang took place, if you just think that matter and antimatter were equal in abundance, then we would not have been created, right? Because
Yeah.
if matter and antimatter comes and touches each other, then everything should be destroyed into energy. Okay? It will just destroy each other if they collide. So at the beginning of the universe, if matter and antimatter were in equal abundance, then this would have been a problem because we would not have been created then. So that is a very big problem also. That is one of the puzzling features. The question that you can ask is that why did the universe create only matter in abundance and antimatter? That is a problem that requires to be solved. It is really a mystery that why matter is in more abundance than antimatter. Because if they were in equal abundance, then our entire history, we would not be there in the history of the universe. So this is one thing that I wanted to discuss about the propagator. So now you have clear idea. I hope that you have a clear idea about what antimatter is and what about these negative energy solutions moving backward in time and things like that. And these are, as I mentioned, that these are not possible in classical physics, so we just throw it away. The advanced Green's function, we don't talk about it, so that is not there. But in quantum physics, these things are there, not in non-relativistic quantum mechanics, quantum physics. Because in non-relativistic quantum physics also you see that only the retarded Green's function features, but it is only in relativistic quantum field theories or quantum mechanics that you require you get these kind of things, or that is negative energy states moving backward in time. So from the next class, what we should try to do is we should try to look at fermionic theories, fermionic interacting theories. So if you have any questions, you can ask me now. Otherwise, you can stop. Huh.
So photons are just bosons.
Yes.
Boson is spin one. So can't we make an approximation from the field? I mean, real stellar field. Real stellar field is the mapping of bosons in number of bosons.
Yes.
Boson field, and so when we are trying to generate a propagated theory of boson field, how do we get it from the bosonic field? Yes.
So the photon field is a bosonic field, but you cannot get it from a real scalar field. So the spin will not match. The photon field has a spin, right? Scalar field photon spin is what? Zero. How will you match the spin?
There is no general description of bosons.
What do you mean by general
I
description?
mean, mass A density is
No, there is. These are basically the representations of the Poincaré group. It will be specified by the mass and the spin or the helicity for massless particles. But you cannot construct a photon field from the quanta of the real scalar field. How can you do that? How can you do that? So the photon field is completely different. When it moves, the electric field and the magnetic field vibrates in the orthogonal directions to the direction of propagation of the photon field. So it has a polarization. Photon field, what is important is, or classical electromagnetic field, it has a polarization. That polarization in terms of, when you talk in terms of photons, that is quantum description, then it has a spin, and that spin is 1.
if you want to construct a general theory of boson or any spin or any mass. How should we
Now you have to take case by case.
we can't
No. How can you do? For each field, you have to, but the general structure is the same. For everything, it will be a collection of infinitely many harmonic oscillators, which are bosonic in nature. The general structure will be the same. But then you can actually, for the photon field, I can actually ask you to do a small calculation and whether check the fact that the photon field indeed has spin 1. You can try and figure it out. Why the photon field has spin 1? You can try and check or figure out how you should proceed to do this calculation. But each field you have to take it separately. Otherwise, it will not work. Yes.
What basic understanding of gauge theory that we have?
Look at the mass. Yeah.
Basic understanding of gauge theory that we have is, so we have a gauge field AB, right? If we add a divergence term to it,
If we have a gauge field,
yeah, and if we add a divergence test term to it, doesn't make a change to whatever.
yes.
So today when you did the separate action, you create a separate action. So that was in terms of, okay, you added something which actually does not change the equation.
This is not changing the equation.
Yeah, and we get the same. We
No, it is changing the equations of motion. We added some term.
yeah.
That changed the equation of motion.
Okay,
Like precisely that.
the final action change the equation. But I mean, how is that linked to this understanding of gauge field that it will not, physics will not change upon adding a divergence? I mean, we should somehow be related to this, right?
Now, the physics will not change, but if you let us come to classical mechanics, if you have an action, add a total derivative term, total time derivative term, then the equations of motion remain the same. Remain the same. You have an action and you add some dfdt. So it's a total time derivative term, and you get that will lead to, it will not contribute to the equations of motion. It will get the same equations of motion. But here, this is not a total derivative term. The action that we have added, that are added,
What my question is, there is no Xi, right?
right?
What I'm looking for is how is this, suppose I make a transformation of Mu plus something, which has 0,
Mu
plus something, which has 0,
okay.
right? So the case will take the. So how is that thing, doing that thing related to the Xi that we are doing?
Related to the Xi term that we have. Okay, what I understand. I have understood your question. What you can basically check is the fact that the term that we have added in the action, the gauge fixing term,
I'm adding in the Mu, I'm changing it.
1 by xi, we have added some term, we get some equation of motion, which is that modified equation of motion with the xi factor. Now you can check that due to the gauge invariance of your electromagnetism, you can choose del mu to be 0. And that condition is perfectly consistent with the equation of motion. That you can see. The equation of motion that you get modified, equation of motion with that psi term, that equation of motion is perfectly consistent with the gauge fixing condition. That you can see. I would ask you to check it. Initially, also it must be consistent with it. By consistency of a gauge fixing condition, what do I mean? What I mean is the following: that you can reach that gauge. That gauge is reachable. Here you get a modified equation of motion by adding the gauge fixing term. You get a xi term in the equation of motion. You can check that that equation of motion is perfectly condition consistent with the initial gauge fixing condition del mu and mu is equal to 0. There will be no clash with this equation of motion. That is it.
We are adding the derivative term. So it will be, we are adding the derivative term. So it will be consistent.
Yeah, it should be consistent, but then also you should check it further, check further things like that. Because when you are adding, you can ask, you can tell me by adding this term you have modified the Maxwell's equations. You can tell me this. This is
I can change the Mu to Mu plus, I mean, Mu
that
plus
is precisely
Mu
that thing
that will be
that even if you have modified the equation of motion by adding the 1 by xi term, but now still you can choose the del mu mu is equal to 0 gauge, and if you choose that, then the equation of motion will again go back to the previous equation of motion. Then there will be no problem. So let us stop here today. Let us continue from what we have done so far from on Monday.